most of the rules you've memorized about determinants aren't independent rules at all. They're consequences of just 3 axioms. Here's a quick distinction. An axiom is a starting assumption we accept without proof. A property is something we derive from those assumptions. Today we prove 3 properties. Property 4, equal rows force the determinant to 0. Property 5, elimination, leaves the determinant unchanged. And property 6, a 0 row forces the determinant to 0. 3 proofs from 3 axioms, all in under 5 minutes. Those 3 axioms are linearity in each row, sign flip when rows are swapped, and the determinant of the identity matrix equals 1. Here's our toolkit. Axiom 1. The determinant is linear in each row. This means 2 things. First, if you multiply a single row by a scalar t, the determinant picks up that factor of t. Second, if one row is the sum of 2 row vectors, row A plus row B, then the determinant splits into the sum of 2 determinants, one with row A and one with row B. Crucially, all other rows stay fixed during this. Axiom 2. Swapping any 2 rows flips the sign of the determinant. If you exchange 2 rows, the new determinant equals negative the old determinant, and axiom 3, the determinant of the identity matrix equals 1. These 3 axioms are all we need. Everything else about determinants follows from them. Property 4, if a matrix has 2 identical rows, its determinant is 0. Let's see why. Take this 3 by 3 matrix A. Rows 1 and 2 are both 2, 3, 1. Row 3 is 5, 0, 4. Now let's swap rows 1 and 2. Since both rows are identical, the matrix looks exactly the same after the swap. Nothing has changed, so the determinant must be unchanged. But axiom 2 tells us that any row swap flips the sign of the determinant. That means the determinant of A must equal negative the determinant of A. Now add the determinant of A to both sides of that equation. We get 2 times the determinant of A equals 0. Divide both sides by 2, and we conclude the determinant of A equals 0. The matrix traps itself in a contradiction, and 0 is the only escape. This result holds for any matrix with 2 identical rows. That was elegant. Here's one that's even faster. Property 6, a matrix with a 0 row has determinant 0. Take this matrix. Row 1 is 3, 1, 2. Row 2 is all zeros. Row 3 is 4, 7, 5. Now rewrite the 0 row as 0 times the row 1, 1, 1. By the scalar part of axiom 1, we can pull that 0 out in front of the determinant. So the determinant equals 0 times the determinant of the modified matrix, where the second row is now 1, 1, 1, and of course 0 times anything is 0. Done. Now the main event, property 5, subtracting a multiple of one row from another leaves the determinant unchanged. This operation is elimination. Subtracting L times row 1 from row 2. Start with the 2 by 2 matrix where row 1 is AB and row 2 is CD. After elimination, row 2 becomes C minus L times A, D minus L times B. We need to show the determinant doesn't change. Here's the trick. We split row 2 into 2 additive pieces. The pair C, D plus the pair negative LA, negative LB. Now we apply axiom 1, linearity in row 2 lets us split this into 2 separate determinants. The first determinant has row 1 as A, B, and row 2 as C, D. The second determinant has row 1 as A, B, and row 2 as negative LA, negative LB. Now let's focus on that second determinant. Row 2 is negative L times AB. By the scalar part of axiom 1, we can pull the factor of negative L out of row 2. That gives us negative L times the determinant of the matrix with row 1 AB and row 2 AB. But now look, both rows are identical. Property 4 tells us that whenever 2 rows of a matrix are the same, the determinant is 0. So the determinant of AB, AB equals 0. Right? And negative L times 0 is just 0. The second piece vanishes entirely. All that remains is the first piece, the determinant of A, B, C, D, the original determinant. And this completes the proof. Row elimination changes nothing about the determinant. Let's verify this with actual numbers. Consider the matrix with row 1, 3, 1, and row 2, 5, 4. The determinant is 3 times 4 minus 1 times 5, which is 12 minus 5, which equals 7. Now let's perform elimination. Subtract 2 times row 1 from row 2. The new row 2 becomes 5 minus 2 times 3, 4 minus 2 times 1. That's 5 minus 6, 4 minus 2, giving us negative 1, 2. So the new matrix has row 1, 3, 1, and row 2, negative 1, 2. The new determinant is 3 times 2 minus 1 times negative 1, which equals 6 plus 1, which equals 7. Same answer. Both determinants are 7, confirming property 5. Row elimination does not change the determinant. Now, here is one critical distinction you must keep straight. Elimination, that is, subtracting a multiple of one row from another, does not change the determinant. But row scaling, multiplying an entire row by a constant, does change it. The determinant gets multiplied by that constant. Do not confuse the two. These are fundamentally different operations. On the left, we have elimination, row 2 minus L times row 1. This leaves the determinant unchanged. On the right, we have row scaling, multiplying row 2 by k. This multiplies the determinant by k. These two operations are not the same. Notice the large not equal sign between them. Property 5 matters enormously because Gaussian elimination is built on exactly the elimination row operation. Here is the full pipeline. We start with any matrix, apply elimination steps to reduce it to upper triangular form. And since elimination preserves the determinant is undisturbed throughout. Once we have an upper triangular matrix, the determinant is simply the product of the diagonal entries. Property 5 enables this entire pipeline. It is the bridge from abstract axioms to practical computation. Let's step back and see the big picture. From just 3 axioms, here is everything we proved. Start at the top with our 3 axioms. Axiom 1, linearity in each row. Axiom 2, the sign flip rule. And axiom 3, the determinant of the identity is 1. Now, axioms 1 and 2 together give us property 4. If a matrix has 2 equal rows, its determinant is 0. Axiom 1 alone gives us property 6. A 0 row means the determinant is 0. Then, axiom 1 combined with property 4 gives us property 5. Elimination preserves the determinant. From property 5, we get a powerful application. Gaussian elimination becomes our main computational tool for determinants. And from property 4, we get another key result. Singular matrices have determinant equal to 0. Notice what happened here. A small set of axioms generates an enormous amount of structure. The determinant is not a grab bag of disconnected rules. It is a tidy interlocked logical system where each property flows from the ones above it. Properties 7 through 10 fall into place just as cleanly from this same foundation.